Hello students, welcome back to the session. In the last session we had said we'll start with a new chapter. We had ended web designing in the last session. In this session we are going to the beginning, that is chapter 2. Hopefully the colleges may reopen on the first week of September. If not, so we are starting the second chapter. I was waiting to start this chapter when the college reopens, but as it hasn't, so let us start without wasting any time. The second chapter is Boolean algebra. This is an important chapter for the concepts, and this chapter carries a total of 9 marks. You have two 2-mark questions and one 5-mark question. Okay, so it is a total of 9 marks. Now, what is Boolean algebra? Boolean algebra is a symbolic system of mathematical logic that represents the relationship between objects. It was invented by George Boolean of England in 1854, and later it was refined by other mathematicians and applied to the set theory. Now Boolean algebra is of significance to the theory of probability, geometry of sets, and information theory. It also constitutes the base for the design of circuits that is used in electronic digital computers. Now, this Boolean algebra, as we said, it deals with the design of electronic devices. One of the major factors in digital is your logical statements. So what is this logical statement? Logical statement means this is a statement that can be answered in the form of either true or false, that is on and off. But there are certain rules of Boolean algebra that is used to evaluate these logical statements. Whatever the statements that you are going to give can be represented in a form of a table. These statements which can be represented using a table is known as a truth table. So a truth table is a mathematical table. A truth table is a mathematical table that contains all possible combinations for the input variables and possible result for each combination. So a truth function is a function formed using a set of truth values. Now let us learn in detail about this truth table later. For now, let us see what is a Boolean expression. A Boolean expression means it's a combination of the values that you are going to make use of. That is a combination of operators, and operators is an expression, as you have learned last year. But Boolean expression is a combination of the variables along with the operators that you are going to use. And the simplification of Boolean expression is helpful to design an efficient logic circuits. So such problems, whatever you have, we solve using binary values. Remember, we use binary values in this Boolean algebra, that is 0 and 1 or 0 or 1. That means the status of an expression, that the result of an expression or the variable must be in the form of either 0 or 1. Therefore, remember this point. Therefore, Boolean algebra is also known as switching algebra. Okay, this is also known as a switching algebra. Now, there are two terms that you are supposed to know in Boolean algebra, that is tautology and fallacy. This is one of the important 2-mark question. What do you mean by tautology and fallacy? An expression which is always true. An expression, let us go for this later. An expression that is always true is called a tautology. Whatever you do, the result will always be true. True is represented as 1. True will be represented as 1. Okay. Now, for example, take the value p and then p bar. We'll know this later. P plus p bar is always 1. As we said, tautology, true. So, if p is equal to 0, then p bar will be 1. So, p plus p bar, that means 0 plus 1. 0 plus 1 is 1. Right? And then, if you take the value of p as 1, then p bar will be 0. That is the opposite. So, p plus p bar is equal to 1 plus 0. That is again 1. So, the result is always 1. The expression which always has the result as 1 is known as tautology. That is true. Result is always true. Then we have fallacy. Fallacy means an expression that is always false is called a fallacy. Now, as an example, the same example, let us take p into p bar is always 0. We said p plus p bar is always 1. In the same way, p into p bar is always 0. 0 means fallacy or false. This is represented as 0. Okay. Now, if p is equal to 0, then p bar will be 1. So, p into p bar, that is 0 into 1. 0, 1 is 0. Right? In the same way, if p is equal to 1, then p bar will be 0. So, p into p bar equals 1 into 0 is again 0. So, it is always false. 0 into 1 is 0. Right? So, this way we are proving that fallacy means the result is always false. This is about tautology and fallacy. Keep in mind, it is a very important question. And next, there are certain rules that you are supposed to follow in Boolean algebra. Rules in Boolean algebra. So, what are those rules? These are very important rules. One thing is, the variables or the values that you are using in Boolean algebra, variables can have only one value. Okay, it should be either, we are talking, when you are saying 1 and 0 means it's binary values. Okay, binary 1 that represents high, or binary 0 means low. 0 means off, false, low, anything can be there. 1 means high, true, on, in this way. So, you can use only zeros and ones in Boolean algebra. And the complement of this variable, complement of a variable is represented by a over bar. Okay, as we said, complement means the opposite. As we said earlier, a is a variable. Okay, a is a variable, and complement of A will be A bar. So this is the complement. If A is equal to 0, then A bar will be 1, the opposite, because we are using only zeros and ones, no other values. Binary means 0 and 1. You have learnt about the binary number system in the previous class, right? So 0 and 1s are the binary values, no other variables. And one another term rule is ORing. You learn about this later. What exactly do you mean by OR? Just say ORing of 2 or more variables is represented by a plus sign between them. Okay, for example, you have two variables A and B. If you are ORing them, then we are saying ORing of A and B means A plus B. Okay, if it is two variables A, B, C, then we say A plus B plus C. This is what you mean by your ORing. These are the logical operators we'll learn later. Then ANDing. ANDing of two or more variables is represented by a sign between them. Okay, dot. That means if it is A and B, if you have two variables A and B, it is represented as A dot B. If you have three variables A, B, C, then you are going to represent it as A dot B dot C. Okay. Sometimes in mathematics you might have learned we represent it as ABC also, that is A into B into C. It can also be done in this way also. So now let us go for this logical operation that we have learned last year. We are going to repeat this again. An operation which uses the logical operators like and, or, not is known as logical operation. An operation which uses the logical operators like not, and, or is known as logical operation. So let us learn these logical operators and operation now. Now, not operation. This not operation is a unary operator. That is, I think you have learnt about the types of operators in the last first year class. Unary operators means that operates on only one operates on one operand is known as a unary operator. So this operator operates on one input variable and changes the truth value of that variable. So it operates, this in explanation is this, or the definition, it operates on one input variable and changes the truth value of that variable. So that is the reverse of the input is the output for that operation. Example, you have a variable x, then the opposite is x bar. If this result is true, then if x is true, then x bar is false. If x is false, then x bar will be true. So the opposite. When we said the truth table, you are saying input and output. This is a single, it operates on a single variable. So this is x means this is not x. Okay, so if it is false, this will be true. If it is true, this will be false. This is known as your truth table. We can also represent it in the terms of variables, that is binary operators. If it is 0, result is true, or 1. If it is 1, the result is 0. So this is about your not operation. We'll learn about the rest of the operators in the next session. Thank you.